Hello.
Hi,
Hi.
how are things, Douglas?
Good. How are you?
Tired.
Yeah.
Monday, always a little bit tired. How'd your weekend go?
Oh, it was actually pretty good. I got a lot done.
You did?
Yeah. How about you?
Um, I watched the Seahawks win, which is good.
Oh, nice.
If you're a Seahawks fan, if not, then that won't interest you one little bit. I don't know. Are you a Seahawks fan?
Yeah, I am, but I don't usually watch sports.
Okay.
Yeah.
But you got a lot of stuff done, so you keep them on top of you. You know, the first week is very hectic, so it's nice that you feel like you're not
Yeah.
overwhelmed, like you've got your grip on it.
Yeah. Um, yeah. Uh, could we go over the problem that the other student went over? I tried to take notes on it, but my Wi-Fi wasn't like very
Um, I
helpful.
don't recollect which question we're talking
It
about
was
here.
using the trapezoidal rule, the midpoint rule, and Simpson's rule for like the last two problems for 7.7.
Okay, gotcha. Okay, so I'm going to go into 7.7 and um, let's get a.
So I've done it. So I've used Desmos to try and do it graphically. I did it on my
Yeah, I
table,
wouldn't do it that way. That would probably. Um,
but it gave me like different answers, and so it was really like difficult to understand like
yeah.
which one was which.
Okay, so we're talking 7.7 here. Agreed?
Yep.
And
Yeah.
it's questions 4 and 5, or 3 and 4, or whatever the numbers are.
3 and 4. Yeah.
Okay, so there's three. Okay, and then basically the same thing, but with a different function for 4, right?
That's right.
So if I can just show you how to do, say, one of them, you follow the process for the second one.
Yep.
Okay. Okay. So this is me doing question 3. You'll see it in a few seconds. I'm just
Okay.
writing it down. Actually, I can show you me writing it down. I can do the screen in 2 ways, so we can make that happen. So in question 3, we're being asked to estimate the answer for the integral, the area under the curve between 0 and 2. It's a cube root. And in my question, it's a 2 plus cosine x. But that 2 might be 4 or 10 or something when you do it, because the Weber sign moves things around. And we're doing it with 4 strips, which is a little bit awkward, but that's fine. And we're being asked to do a trapezoid, a midpoint, and a Simpsons rule, okay?
Right.
Right. So, first thing before I even look at that entire process is, for 4 strips, starting at 0 and finishing at 0.5, I need to find what are called the ordinates, right? So they're going to be 5 points, because when you have 4 strips, you have 5 coordinates.
Right.
1, 2, 3, 4, and 5. I kind of know who the first and last one is, because it's pretty obvious. I
Mm-hmm.
just need to figure these guys out. And for each one of those, I need to find the value of the function. This particular story, good grief, wants 6 decimal places. That's going to be a bit of a pain, but I'll do the best I can. So I need to do, let's change colour. I need to know who delta x is. So it's b minus a over n. So it's pi upon 2, take away 0, divided by 4, and that is pi
Over
upon
8.
8. So I'm going to go 1 pi upon 8, 2 pi upon 8, which is a quarter, 3 pi upon 8, and then 4 pi upon 8. So I know it matches. We got all those guys. Those
Mm-hmm.
guys, I now need to find out what the value of the function is. And since I'm going to round off to allegedly 6 decimal places, that's going to be a bit of a pain. I'm going to try something here. No, I won't. I think if I did the table setup method, it won't give me 6 decimal places. Maybe. Let me try it.
Yeah.
I can
And
only,
Desmos, like graphically, it only gave me like 4 decimal places,
yeah,
and
and that all that's going to go there is that your answer will be correct to 4, but it won't necessarily be correct to 6, because it won't have 6 in it for starters. So I'm going to go and look at this guy and put in our function. So y equals the cube root, so that's a bracket, 2 plus cosine of x, and then raise it to the power, put a bracket around it, 1/3. It's a bit clunky, but it's the quickest way to do a cube root, 1/3 power. And then I'm going to go to table setup. I'm going to start at 0, and I'm going to do a delta of pi upon 8. And what that's going to do is it's going to basically do all these calculations for me without me having to do them one at a time. So second table setup gets you this guy. Then second table, and darn it, it's 4 decimal places, so I can't do the shortcut. I was hoping I could do it that way. I'm going to have to do it the boring way. Basically, you plug in 2 and you get the answer. So you're going to go bracket 2 plus the cosine of 0 raised to the power of 1/3. And that answer is 1.44 4957. Well, 496. Okay, that's plenty of accuracy. So you basically do the calculation, you write it down. It's really a laborious process, it takes forever. But we got the first one, right?
Yep.
Right, so the next one I would do would be pi upon 8. So I'd go 2 plus the cosine of pi upon 8, close brackets, raised to the power of 1/3, and I'd get another number. I'm just going to pretend, really pretend, that it's 1.2, 1.7, 1.9, and 2.5. I know it's not, but whatever it really is, right? Just so we've got something to work with. Now, once you've got this fella done, you'll be able to do the trapezoid rule and Simpson's rule.
Right, yeah, that's what I did.
So as long as you use these numbers to 6, I'd probably do 7 or 8 places, then you should be able to match that. It should work. So if you're doing trapezoid 4, it's going to be delta x over 2, 1 of the first guy, 2 of everybody else, and 1 of the last guy. Okay. Right. So it's going to be 1 of them, 2 of these, 2 of these, 2 of these. In case you're wondering, he's x0, he's called x1, x2, x3, and finally x4, and 1 of the last one. So it's going to be delta x, which is this fella, divided by 2, a bit messy. 1 of these guys, 2 of these guys, 2 of these guys, 2 of these guys, and 1 of the last guy.
Yeah.
And you just add that lot up. Well, I'd probably find out what this fella is, and then find out what this fella is, and then you multiply them together, and you get 1.2, 3, 4, 5, 6, 7, 8, 9, whatever you really do get.
Right.
And then you go 1, 2, 3, 4, 5, 6, finishes there, round up. So your answer would be 1.2, 3, 4, 5, 6, 8, and whew, you're done.
Yeah, that's what I've been doing, but
I don't know if it's not working. You're doing everything right. So the only thing that can be coming, it's hard to tell. Was your calculator in radians or degrees? That could have screwed
it was
you.
in radians.
And that's not that.
Wait, what?
Yeah, it should be in radians. So if it was, you're fine, Douglas. The only other places you could go wrong is simply just because there's so much detail here that there could have been, instead of you doing 4-2, you do 2-4. You just typed the wrong digit in somewhere.
Yeah. Or
you didn't do enough accuracy here. And because you don't do it, because you want 6, it means you have to build up an awful lot of, it's better to be working with 7 just so you can round off to 6. Right, yeah. And so that's going to be that. Now, if you want to do the Simpsons one, with 4 is going to be delta x over 3. The first guy, 4 of the second guy, 2 of the next guy, that's the 1, 2 of the next guy, 4 of this guy, and then 1 of the last guy. And that's the pattern. For Simpson, it's 1, 4, 2, 4, 1 is the pattern that you use.
Mhm.
But it's the same numbers you're going to double and multiply by 4, and it's the same numbers that you're going to add up. The difference here is it's going to be multiplied not by delta x, but delta x divided by 3. And as long as you're careful, you'll get the right answer.
Yeah.
I think everybody, pretty much everybody is here, so we'll get started. We're kind of in a nice place now. You're probably the same as me. I'm kind of glad that Simpsons and trapezoid and all that boring number crunching is over with. And now we can find exact values for area under curve, but we can do it using what's called the fundamental theorem of calculus part 2. And essentially it says if you want to find the area under curve from x equals a to x equals b of any function, f of x dx, then you just find the antiderivative evaluated at b, and you take away the antiderivative evaluated at a. And what might have took you 20 minutes might only take you 2, right? It's very efficient. And no cheating, so you're not allowed to look at your notes from last time. But here is a whole list of functions, and right next door to them, we're going to do the antiderivatives, because you have got to be kind of fluent on these. You got to just know them like that. Boom, boom, boom. You can't keep saying, oh God, I'm going to have to look at that one up again, and I'm going to have to look this one up. So since I've got a kind of order set up here, e to the x, antiderivative, just shout it out. What's the antiderivative of e to the power of x?
E to the x.
Okay. Be careful. Antiderivative of sine x. Just shout it out, anybody.
Negative cosine.
You got the negative exactly. So this one's going to be easy now, isn't it? Antiderivative of cosines.
Sine.
You're not allowed to look at a sheet. You have to be doing this from memory. Antiderivative of secant squared.
Tangent.
Good one. Weird one. Antiderivative of 1 over 1 plus x squared.
Inverse tangent.
Well done. When you look at those two together, do you see how totally unlike each other they are? I mean, that guy and that guy don't look like they're even in the same planet, right? But aren't their antiderivatives very similar? They're not the same. I mean, the tan of x and the inverse tan of x are different, but they are kind of close, aren't they? At least, in my opinion. Okay, what's that weird one?
Inverse sine.
Yeah. What about this one?
ln.
Yeah, here, ln's. And last but not least, I guess, what's that one?
Tangent squared.
Oh, that'd be interesting. Nope, but it's a good guess.
Wasn't it secant?
Yeah. Now, is that the only standard integrals? No, there's quite a few bits and pieces. If you come across a function that you need to find its antiderivative and it's not in this list, it does exist. You just might have to go hunting for it. You might have to go and search online for it. You might have to go and look for it, but it will exist. I mean, off the top of my head, cosecant squared, for instance, is negative cotangent, right? Cosecant cotangent is negative cosecant. There's just two off the top of my head. Now, I'm not writing every possible one in the world down, because if I did this, this table would become impractical. These, however, are pretty common. So these are the ones you should be good at remembering, because these guys are going to be the ones you'll see pretty much 90% +% of the time. So if you know these ones, then you know it's easy to fix the others when a weird one turns up. So far, so good. Any questions? Couple comfortable with these guys? So the devil is in the detail. So we are going to look at finding various what are called indefinite integrals here, or definite integrals, I should say. A definite integral is for a guy that looks like this. If you're being asked to find the area under a curve of a function, in this case this function here, and you're told a start number and a finish number, it's called a definite integral. When we are finished, won't it be, this will be equal to 42, right? It'll be equal to a definite thing, right? That's what's called a definite integral. So let's see how the process works. You have this guy here, right? We take the terms and we find their antiderivatives and we evaluate them at x equals 0 to x equals 1. Okay. X cubed belongs in the power rule, which is probably the most common one you'll ever deal with. And the rule for that is you add 1 to the power and you divide by the new power. So the antiderivative of x cubed is 1/4 x to the 4. You agree? You add 1 to the power and then dividing by 4 gets you 1/4. Now you should be able to check that it's right. If you differentiate 1/4 x to the power of 4, don't you end up with x cubed? Right? Remember differentiation of 1/4 x to the 4? It works. What would 4x get me? The antiderivative of 4x. How many squareds?
2.
2. I just have a special rule for 7. What's the antiderivative of a number like 7?
7x.
Yeah. So my special rule is if it's a number, just stick an x at the side. Now, once you get to that stage, you basically are going to find what it's equal to when x is 1, take away what it's equal to when x is, in this case, equal to 0.
Hey.
Well, question?
Don't we have to add c to the end?
Technically, we don't need to when it's a definite integral. And you might say, well, let me finish this with numbers and then I'll show you why we don't bother.
Okay,
But
thank you.
technically it should, right? So I'm going to plug in 1. So it's going to be 1/4 1 to the 4 plus 2 lots of 1 squared plus 7 lots of 1. And here's something I typically do, and I think you should. See if you know, because the number is 0 very often, and you know that all of these are 0, can't we just put in a big 0 and say, I'm not going to write all this 1/4 0 to the 4 and, you know, a whole load of writing that's just 0. So it saves a little bit of working, doesn't it? If you just do a blanket, I know it's going to all equal 0, so why bother, right? We cool with that? X 0, 0, 0, the whole thing's still 0. Now this fella here gets us 1/4, this guy gets us 2, this guy gets us 7, and it might look like the correct answer should be 9 1/4. So the area under this curve between 0 and 1 is exactly 9 1/4. But we don't like 9 1/4. We don't even like 9.25. I mean, it's 99% correct, but we don't like it. Shouldn't this guy in the math world be written as an improper fraction? And that's the guy that I would expect you to type into the box. Because in your homework, in WebAssign, it would just look like this. Right? So all you would do in WebAssign is that. Even although there's a whole chunk of working that you needed to get there, all that WebAssign expects you to tell it is the final answer. We're probably aware that it does that a lot. Now, someone said, but shouldn't there be a plus c? And technically there should be. So imagine this had plus c in it, right? Then wouldn't there be a plus c here And wouldn't there be a plus c here as well? What would happen to that c if you take away that c?
It'd be 0 technically.
Right, and won't that always happen, no matter how ugly this function is? If you find its antiderivative and add a c, won't you get a plus c in the first thing, take away the same plus c on the second thing, that they cancel out? So what we do in math very often is we take the shortcut, right? So technically there's a plus c in both those, right, from here. But we don't even write it there because we know it's always going to disappear. So they just ignore it. I mean, if you really felt like you wanted one, I don't think there's a big problem with it. Do it. But won't they disappear at the end anyway? Any other questions? Are we good? Don't know if I've shown you this little trick. Let's do it right now. Let's suppose I got one of these kind of calculations, right? These things up here, but let's suppose it's got more fractions than just a single one like that. So let's suppose it was 2/3 plus 8 take away 4/5, right? So imagine that was the calculation. 2/3 add in 8 take away a 4/5. Now if you do this on your calculator, you get a ridiculous decimal. But if you then hit the math button and option 1, you can turn it into a nice improper fraction, 118/15. You see, that takes away a lot of the strain of, you know, dealing with fractions in your calculation. You seen that trick before? Good. So that's what I would choose if I was doing these questions. Okay. So I guess I'll call that example 1. So what am I going to do in example 2? Well, I'm going to do quite a few things. I'm going to do the integral from 1 to 3. That's not a big thing. And then I'm going to do u plus 3 2u take away 4 du. We normally like integrals to have x's with a dx, but really the letter, the variable, doesn't matter. Do you know that there is exactly the same meaning as that? Would you agree? That the letter of the variable doesn't really have any fundamental importance. It's just a placeholder, right? So here's the second piece of this puzzle. How do I find the integral? In fact, I'm probably going to stop using the word antiderivative, or at least I'll peter out using it, and I'm going to start using the word integral. So I'm going to say, how do we integrate that? Rather than say, how do we find its antiderivative, right? Interchangeable, right? They mean the same. But antiderivative is a bit of a mouthful, and integral is a little bit cleaner. Anyway, any suggestions for how I would tackle this question? Right
Simplify
now,
the two terms.
okay, so by that foiling all out?
Yeah.
Agreed. So it would end up being eventually 2u squared. That would get you 6. So plus 2u take away 12. I basically foiled that out. So I'll put a little note. Right. So can you imagine I foiled it out and I got this, and hopefully I did it in my head correctly. Now at this point, shouldn't we then be able to just add 1 to the power, divide by the new power, add 1 to the power, divide by the new power, and won't negative 12 just get me negative 2u, and I'll evaluate it at u equals 1 and u equals 3, and then I'm going to do my fancy ... thing. To save time, because we have a limited time and I don't want to spend it doing something that is just pretty obvious, I hope pretty obvious, wouldn't I just evaluate this when u equals 3? And the answer would go here. Oops. And then wouldn't I evaluate this thing at 1? So plug in 3, 3, and 3, get the whole answer. Plug in 1, 1, and 1, get the whole answer. First answer, take away second answer, boom, you're done. Is it okay me missing out the number crunching part that you finish with? Because it's really just grab your calculator and start hitting buttons, isn't it, by that point? Okay, here's your next puzzle. So this is how you're going to deal with that one. How are we going to deal with that one?
I mean, yeah, probably the same way, right? Just square both terms or square the term.
Yeah. I hope you don't make the dreaded mistake that when you square this, the answer is p squared plus 9. Isn't it actually p squared plus 6p plus 9? Because technically, doesn't that mean p plus 3 times another p plus 3? And if you FOIL it out, you do get a middle term. So nobody here is going to do the p squared plus 9 mistake, right? There is a 6p there. Now, if we do the antiderivative, it's 1/3 p cubed plus 3p squared plus 9, evaluated at p equals 2 and at p equals 4. That's 1/3 4 cubed plus 3 times 4 squared plus 4. Take away 1/3 2 cubed plus 3 lots of 2 squared. Nobody noticed. I forgot the p there, didn't I? It's 9 gets you 9p. And the last guy is 9 times 2. And now I'm dotting that one because it's just a whole load of number crunching stuff. Did you all notice my deliberate mistake of the 9 should have been a 9p?
Yeah.
Yeah. Well, let me tell you right now, there's a kind of rule here. I make mistakes, not deliberate mistakes, I just make mistakes. And your job is the minute you see me starting to do something, is say, wait a minute, shouldn't that 9 be a 9p? And I'm going to go, oops, did you all catch that deliberate mistake? And then we will continue. Because not all of you will have noticed that mistake, and then you will go back and you will start second guessing yourself. And you'll be saying, yeah, I thought 9 should turn into a 9p, but it looks like in some questions, it just ends up being plus 9 again. And now I'm confused because I thought I knew the rule, but now I'm not so sure I do. And instead of doubting yourself, well, you just doubt me. Hey, he forgot to stick the p, didn't he? It should have been 9p or whatever the variable is. So, FOIL. But this example. Sometimes the simplest ones are the ones that will cause you the greatest grief. And you're going to say, wait a minute, there aren't any square roots here. You should have told me square root of x and then what its antiderivative is so I could find out what that guy is, right? Seems reasonable, but that's actually not what you need to do, because there are going to be many situations that don't fall into this category, at least the way they're originally given to you. But if you work at it, you can make it, even this guy, you can make it a power rule. Do you know the power rule that we've been using up to this point in time has been pretty simple ones? The antiderivative of 5x squared, right? The integral of 6x cubed. Do you know things like that? Add 1 to the power, divide by new power. I'm going to do it for this one. I just have to realize that isn't the square root of x also a fractional power? Right? X and a half. And does this rule work when the power isn't 3 or 2 or 20. Yeah, it works. And the rule is add 1 to the power and divide by the new power. Now, it makes it a bit messier. I totally agree with that. If you add 1 to the power, don't you get 3 halves instead of 1 half? Do you notice we don't call it 1.5, right? We call it 3 halves. Same thing, but we call it 3 halves. What do you do if you want to divide by 3 halves? What's the equivalent mathematical thing to dividing by 3 halves?
Multiplying by 2/3.
Right, so you go times 2/3. And you may actually do this line in your head, but do you notice that you now get, after a little bit of work, don't you get that? Agreed? But for calculation purposes, and also because of algebra, style points, shouldn't you always try and write your answer in the same form that it started off at? So shouldn't this be converted into some kind of square root? So let's find out. 3 halves is the square root of x cubed. You agree? 3 halves is the square root of x cubed. And then, in case you're wondering, we're still going to evaluate it at x equals 0 to x equals 2. So it's 4 lots of the square root of 2 cubed. That's the first one. Take away, well, 4 lots of none. Take away a big fat nothing, right? And that becomes 4 lots times the square root of 8. Take away nothing. I'm not sure why I wrote take away nothing. And the answer should be 4 square root of 8. Nope. You can simplify, sometimes anyway, can't you simplify square root of 8? And the rules of the game are always to write your answer as an exact value, which this is, but in the simplest version of that exact answer. So nobody would say 4/8, right? Everybody would say, oh, that's a half, right? That's a simplified version. What does the square root of 8 become?
2 root 2?
Yeah. Somewhere in math, good grief, where is that? Somewhere in math 99, I believe. Didn't you do simplifying square root of 20s and simplifying square root of 8s? Remember doing those, guys? I'm way back in, well, a year ago, wherever you did it, right? So 8 is 4 times 2. The square root of 4 gets you 2, so it's 2 root 2. That makes the final answer, and it is the final answer, as 8 root 2. Now what I'm about to show you is how you can let your calculator check, and it is only a check, this answer, right? So first thing I'm going to do is find out what 8 times the square root of 2 is. And it's roughly 11.3137085, right? Now I'm going to go up here. I'm going to type in 6 square root of x. So that's the function. I'm going to go to the window. I'm interested in getting the answer, from 0 to 2. So I'm going to start with a 0, an x min. I'm going to finish with the 2. So far, so good. And now I'm going to do zoom 0, which basically just draws the thing. So that's what 6 square root of x looks like. And you can imagine that where my finger is, isn't that the area that we're trying to find? Now, if you go second calc, do you see a guy there called number 7 that looks like our integral symbol? Hit enter. I'll type in 0 as the start, right? Lower limit. I'll plug in 2 as the upper limit. And when I hit enter, this decimal, near enough, will appear. Now, if this guy matches that guy, I must have done this correctly. If this guy does not match that guy, then somewhere in here I screwed up. Maybe I didn't divide by the right amount. Maybe I lost a number somewhere. Maybe I forgot to put a P instead of 9P, right? Whatever it is I did, these will not match, and therefore at least I know that it's wrong, and I should go and search through my working to try and discover what I've done wrong. Is that kind of cool? Little check. Of course, you can't use that, because if you type that into the box where your answer goes, won't WebAssign just say you're wrong? Because WebAssign wants you to write this down, the exact value. So you can't say, oh, I got a great way, I can just do all my homework like this. Right? No, none of your answers will work. But you can use it to check. Any questions about that? All I'm trying to do here is I'm trying to build up as many different situations as I can, so that when you see a situation that isn't a kind of standard one, then you've got some kind of way to do it. So here's the next fella. We need to find this indefinite, this definite, I keep saying indefinite, this definite integral. We need to get the area under that curve. Obviously, I can't start finding antiderivatives right now. It's not in the format that we need. Come on, help me out here. Don't need to do the whole thing, but at least tell me something I could do.
The next step, try to get everything into like the same like exponential values, or just into exponents.
Okay, so in this case, it's really just the square root of x that needs to be fixed.
Yeah,
Okay?
so it'd be x to the 1.5 power, yeah.
Now, a lot of the things that you've done in your math career, like the square root of 8 was 2 root 8, foiling, right? That's just to mention a couple of things, right? Don't we then have to say, oh God, how do you multiply x to the half and x squared? Well, I'll tell you right now, the answer is not x to the power of 1. That's not how you multiply them. X squared times x to the half. And in fact, I wouldn't normally write this line down, but I'm going to do it this time. You're going to multiply each of these two pieces by x to the half. So what do you get if you multiply x to the power of 2 by x to the power of 1/2? What single power of x do you get?
Next to the 5 halves.
Right, 2.5 is, you know, maybe what you think in your head, but even if you do that, well, you know, isn't the rule you add powers together in this case, right? You add exponents. So x cubed times x squared is 2 add 3 is x to the 5, right? Now, in the second one then, won't you get 3/2? Oops, where's that come from? There. 1 1/2, 3/2. Now we can use the power rule. Add 1 to the power. Well, if you add 1 whole amount to 5/2, you get 7/2. And then you divide by that new power. What fraction goes here that represents dividing by 7/2?
2/7.
You know, it's a kind of reciprocal thing going on. This one. Add 1 to the power. If you want to divide by 5/2, isn't it the same as multiplying by 2/5? And 2 times 2/5 is where 4/5 came from. And then you can evaluate this from 1 to 3. Well, I wouldn't do it quite yet. wouldn't I call that the square root of x to the 7? And I'd take this fella and I'd call him the square root of x to the 5. And then I'm going to do dot, 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 dot. Because trust me, that would be one ugly square root and that would be one ugly square root. But it's okay if the answer is 2,000, 2 sevens, the square root of 43,311, add 4/5 the square root of 272. It's okay to be ridiculously ugly answers because it's still correct, right? It's just a ridiculously ugly correct answer. So you'd plug in 3 here and here and get an answer. Plugging in 1s would be easy because wouldn't that just be 2 sevens add 4/5? And that wouldn't be too bad. But the 3 certainly would be really messy. Are we cool with that? Not sure if my numbers are correct anymore. Let's look at this definite integral. It's not really ready for finding antiderivatives, is it? So we have to go back to math, I think it's 94, 94, 99, I can never quite remember, where we take this and we have to rewrite it in a different format that will allow us to do an antiderivative. In particular, we need to do it in a format that allows us to use the power rule. So you see the power rule is a lot of questions you're going to end up using the power rule, right? Four on the top over v to the 4. What power of v is that the equivalent of?
Negative 4.
Yeah. Do you remember that one? Square roots are halves. Something over v squared is v to the -2. So a guy in the bottom is a negative power, essentially. You remember that guy? Now, there's a different little weird thing that's going to happen next. We are going to do the power rule, but we are going to be really careful when we do the power rule. Isn't the power rule add 1 to the power and divide by the new power? Great. So here goes. What do you get if you add 1 to this fella? If you add 1, yeah. Do you know what the mistake people make? They call it -5. You see what I'm getting at? -4, add 1, you now have -3. Now you're going to divide by that new power. Are you happy about how this became that? Do you notice that it's now 4/3 and it's negative because dividing by -3 created this piece? This is not good for calculations. So I'm going to use the make me look like the original. Would you agree that if you want an exact value, right, wouldn't you probably have to create, this is going to have to be converted into this, right? Half powers become square roots, that kind of thing. Negative powers become fractions, that kind of thing. Now in this case here, what are we going to do? We're going to go -4 over 3 lots of 2 cubed. That's the first one. Take away -4 over basically 3. And that's 2, 4, 8, 12. So it's -4 over 36. Take away a negative is like adding it, and you get 4/3. Okay. I'm not going to show you this yet. But I will be in a few seconds. Okay. You know that we're going to combine these two guys together? see what it looks like. Negative symbol. Oops. Put it up a bit. Negative symbol. 4 divided by 36. That's how you. Darn it. There, you can see it now. Okay. You won't be able to see what's under here, but you will be at least saying that. So that's negative 436. Add 4/3. Do you see how I type it in? It looks like divisions, but that's the 2 fractions. There's a horrible decimal. Math, choice 1. There's your 11/9. And that's the answer that goes in your text in WebAssign. You see how helpful that's going to be, your calculator, for all the weird fiddly fractions, right? Or if you're great at fractions, I guess you don't need to do that at all. You can do it the usual way.
Wait. Oh. 2 cubed is 8, and 3 times 8 is 24, correct?
Oh, did you all catch that deliberate mistake?
And then could you simplify it down to 1/6?
And then just take over here. And the answer is 7/6. Now, how would I have been able to detect that? Well, obviously I made a mistake and someone caught me. But if I plugged this into my calculator, wouldn't I get an answer that wasn't the same decimal as 11/9? And I would look at my decimal answer. So let me do that. Since I've got a few more minutes, we are going to take that question and we were going to check it out, especially in a test when you don't know if you're right or wrong, because the WebAssign will not tell you you're wrong. It will just take whatever answer you've got when you're in a test, right? You know how in homework, if you're wrong, it has a big red X, I think, and you know where you're wrong and you go and fix it. So I'm going to put this guy in and we're going to prove that it's that fella, right? And not this one. So I go to y equals. It's going to be 4 over v to the 4, but that's just 4 divided by x to the power of 4. Right, we just call everything x. It's going to go from window, start at 1, finish at 2. I'm then going to go zoom 0 to see the thing. So it's a pretty boring curve, as all of them pretty much are. Now I'm going to go second calculate, choice 7. I'm going to start at 1. I'm going to finish at 2. And if we do it correctly, shouldn't it be the decimal value of 7/6? And isn't 1.1 with a whole load of 6s the decimal value of 7/6? It's not the decimal value of 11/9. If I do 11/9, do you see that that answer is not the same? And I would have been able to say in my test, okay, I did something in my head, I must have got it wrong. Oh, that's right, 2 cubed is 8 and 3 8s are 24. And hopefully find it. Are we good? Are you comfortable with what we've been doing so far? Any questions before I continue? Okay. Just checking. So, okay, I've got a few more to do. This is number 7. How about the integral from 1 to the square root of 3 of 2, 1 plus x squared dx? Do you recognize 2 over 1 plus x squared? It's almost exactly this guy, isn't it? isn't the only difference. There's a 2 on the top instead of a 1. So if 1 over 1 plus x squared has an antiderivative of the inverse tan, shouldn't 2 over 1 plus x squared have an antiderivative of 2 lots of the inverse tan? Are you comfortable with what I just did there? Does that seem reasonable?
Yeah.
Right? If that was 20, wouldn't this be 20 inverse tans? If that was -4, I guess it would be -4 inverse tans. So what's the next piece of the puzzle? Well, evaluate the inverse tan at the square root of 3. Take away, evaluate the inverse tan at 1. And this is 142 we're now in. Do you know that there is an angle whose tangent is equal to 1? And that's what the inverse tan gives you. It tells you the angle in your unit circle whose tangent is 1. And the inverse tan of root 3 is an angle whose tangent is equal to root 3. And we need to find what these two guys are so that we can double them and take them away. So I'm going to go for this one, which I think is easier. What angle has an inverse tan of 1?
Would it be 45?
Correct. Do you remember, I'm not going to call it 45 because we use radians in calculus, but you're right, it's 45. Pi upon 4 I'm going to use. You remember that guy? Doesn't he have a tangent of 1? So, 2 lots of pi upon 4. Now, okay, it's not to scale, but I'll do it anyway. These two triangles are very helpful for answering these questions. They're actually very helpful for answering inverse sines and cosines as well. It's a 1, 1, root 2 triangle, which has 45 degrees, but we call them pi upon 4. Do you know what the two angles that match this triangle are? Do you know what these two angles are?
Not
30 and
30 and 60.
Yeah, and we call that pi upon 3 and pi upon 6. So yeah, you're right, 30 and 60, but we're doing the radian version of them. Right, now, what angle has an inverse tangent equal to root 3? If you look at this triangle, don't you get tangents by doing opposite over adjacents? And if I wanted to get root 3, wouldn't it be root 3 over 1? So this would be the opposite and this would be the adjacent. So from my picture then, doesn't that get me 2 lots of pi upon 3? I think I've mentioned it to all my classes lots and lots of times. Do you know there's nothing in math that you've done, even from Math 94, that you think is baby stuff now and you'll never need to do it again, ever disappears in math. You do Calc 4, and you're still going to have to know what the inverse tan of things like this is, right? You do Diff Eq 2, you're still going to have to FOIL some things and factor some things and turn x to the half, you know, x, the square root of x into x a half. Do you know all those algebra things that we kind of did and put them in a little box and say, okay, that's that, finish with, I'll forget about it now and move on? That doesn't work. You remember Calc, you know, this is a pre-Calc 2, right? This is trig, and you're thinking, whoa, he's bringing out inverse tans from, you know, mid-air. Okay, let's tidy this fella up. 2/3 pi, take away 2/4, which is a half pi. On my calculator, unless you want to do it in your head, it's 2/3, subtract 1/2, and then make it a fraction. And the answer is a 1/6. So you get 1/6 pi. So you might be able to do all the math stuff, and then you get stuck on the, I don't know what the exact value is. And you can't even use your calculators to do this. If you try and use your calculators directly, you're going to have a problem, because all you'll get out of this is a decimal. So let me show you me doing this on the calculator. Oh, I'll just go to the calculator and find out what the inverse tan of 1 is. How hard can that be? You see, it doesn't tell you. Well, who is that? Well, that guy is actually pi divided by 4. Well, I guess if you were really good at memorizing what the decimal versions of standard angles are, you could probably do it, but I wouldn't, right? So you just got to get good at remembering these two triangles, right? This triangle here will get you all the inverse functions and the normal ones. While we're at it, do you know I can use these triangles? Suppose I wanted to know what the sine of pi upon 3 was, right? The sine of pi upon 3, not the inverse sine. Well, don't you go here and you call this guy opposite, you call this out adjacent, call this hypotenuse. Isn't the sine of that root 3 over 2? Right, the sine of pi upon 3 is opposite over hypotenuse. Suppose I wanted to use this triangle to find the inverse cosine of a half. If you wanted to do an inverse cosine, aren't you looking for an angle whose cosine is a half? Isn't the cosine adjacent over hypotenuse? If you wanted a half, doesn't this have to be the adjacent and this guy here has to be the hypotenuse? And what angle has this as the adjacent hypotenuse? It's pi upon 3. So these two triangles contain inside them all the standard angles that you need for sine, cosine, tangent, and all the standard angles that you need for inverse sine, inverse cosine, and inverse tangent. I would like to know the tangent of pi upon 6. Yeah. I'd go to this triangle. I'll put it here. And I'd say, okay, there's pi upon 6. And the numbers don't change, right? They're all in the same place. But from this guy's perspective, isn't the opposite 0 and the adjacent is root 3? And I know for the tangent that it's opposite over adjacent, so I know that it's 1 over root 3. And that is correct, it is 1 over root 3. Is there a better way of writing 1 over root 3? It's called rationalizing the denominator. And what you would do here is multiply by that special version of 1. And there's your answer for the tan of pi upon 6. So that's the shortcut way that you use these two triangles to find every standard angle for sine, cosine, tan, and every inverse sine, cosine, tan as well. So, cool thing to know, to have, you know,